Hello there, everybody, and welcome to our math journey. I'm Daniel, won't even waste your time with a middle name, Valvo, and I'll be your host, guide, and if all goes well, maybe even your acquaintance by the end of these mathematical modules. Now, today we're going to kick it off with something fundamental to mathematics numbers. Let's get started. Unless you've been living under a rock for the past 10,000 years, you've probably heard of numbers. Humans have been working with numbers since the Stone Age, and the number concept is historically the foundation of mathematics. So you've probably heard of numbers like 1, or maybe even 9.99, or 4/5, or one of my favorites, pi. You may have even heard that 789, but that's just a nasty rumor. While numbers might seem simple, dig a little deeper and you'll see there's a lot going on underneath. We'll do just that by examining different types or categories of numbers. The first type of numbers we will look at are the whole numbers. Whole numbers are numbers with no fractional or decimal part. Additionally, they cannot be negative. Simply put, this means the whole numbers are the numbers 0, 1, 2, 3, etc. Next up we have the natural numbers, or the counting numbers. They're usually the first numbers you encounter when you're a kid. We call them the counting numbers because they're the numbers we use to count things. More formally, the natural numbers are the whole numbers 1 and up. Notice that when you learn how to count as a kid, you never count 0 things, so the natural numbers line up with our notion of counting perfectly. For example, if you were counting things at a park, you could count 1 partridge, 2 turtle doves, 3 French hens, or 4 golden girls. Whole numbers and natural numbers are both positive by definition. But what fun would the world be without those negative nellies? The integers are all of the whole numbers with their negative counterparts. So we have the whole numbers 0, 1, 2, 3, etc., but also their negatives, negative 1, negative 2, negative 3, etc. Now you may be thinking, natural numbers and whole numbers compared to what? Half numbers? Fractions of numbers? Great idea, sarcastic man! The simplest non-integer numbers we encounter are the rational numbers. Rational numbers are any numbers that can be written as one integer divided by another integer. In other words, the rational numbers are all of the fractions or ratios that can be made with the integers. So for example, we have 1/2, which we can convert to decimal notation to be 0.5. Notice 1 and 2 are integers, so 1/2 is the ratio of two integers and therefore is a rational number. Or we could have 0.25, which equals 1/4 in fractional notation. Once again, 1 and 4 are integers, so 0.25, which equals 1/4, is a rational number. Another example is 4.12, which is 412 divided by 100 in fractional notation. We also have 1/3, which in decimal notation is 0.33333333 repeating. Once again, because 1 and 3 are integers, 0.33333 repeating, which equals 1/3, is a rational number. Now let's talk decimals for a second. Every number has a decimal expansion, meaning it can be written as a decimal. In particular, every fraction can be written as a decimal, but not every decimal can be written as a fraction. Only decimals that terminate, like 0.6 or 0.89, or decimals that eventually repeat, like 0.788888 repeating, or 64.1232323 repeating, can be written as fractions. Notice the bar above the 8 means to repeat 8 forever, and the bar above the 23 means to repeat 23 forever. Since these repeating and terminating decimals can be written as fractions, that makes them rational numbers. Finally, we can look at the integers. Notice that the integer -7 equals -7 divided by 1, which is a ratio of the integers -7 and 1, meaning -7 is a rational number, and in fact every integer is a rational number as well. But wait, we said that decimals that terminate or get into a repeating pattern are rational numbers. But what about decimals that never get into a repeating pattern? Welcome to the irrational numbers. Let me show you around. The irrational numbers are simply numbers that cannot be expressed as a fraction. Some of the world's most famous numbers are part of this club, including pi, e, and the square root of 2. What do they all have in common? Their decimals never get into a repeating pattern, and they don't terminate, meaning they're not rational, which makes them irrational. Alright, things have already gotten pretty heavy today, but now they're about to get real. The last category of numbers we're going to deal with are the real numbers. Real numbers are all of the numbers in the number line. We will discuss the number line in detail later, but for now, we can think of all the real numbers as simply being every natural number, whole number, integer, rational, and irrational. Examples include 5, -7, 0.312, 1/2, pi, square root of 2, or any other number on the number line you can think of. Now that we've met the whole numbers and the natural numbers and the integers and the rational numbers and the irrational numbers and the real numbers, we can start to ask how they all relate to each other. Let's make a family tree or more like a blob to figure this out. Here's how all of our different types of numbers fit together. For example, since the natural numbers blob is inside the whole numbers blob, that means the natural numbers are in the whole numbers. Or in other words, every natural number is a whole number. Now we'll do some examples. Let's start with 2. 2 is a natural number, so it's in the natural blob. But seeing how the natural blob is contained in all of these other blobs, we can see that 2 is also a whole number, an integer, a rational number, and a real number. Similarly, 46 is natural, so it's also a whole number, an integer, a rational number, and a real number. How about 0? 0 is not natural, but it is a whole number. Then we know it's also an integer, a rational number, and a real number. Then we've got 1/4. 1/4 is a rational number, and since the rational blob is contained in the real blob, 1/4 is also a real number. How about 6.675? The decimal terminates, so we know it's rational. Then, since it's rational, we know it's also real. Lastly, let's try the square root of 5. The square root of 5 equals 2.23606, where the decimal keeps going forever but never repeats. So the square root of 5 is irrational. Since it's irrational, it's not rational or an integer or a whole number or a natural number. It is, however, real, since the irrational blob is contained in the real blob. Hence, the square root of 5 is irrational and real. As promised, I will now discuss the number line. But first, let's think about where lines come up in our day-to-day life. You could wait in line at the grocery store, or the coffee shop, or if you're in the UK, there may even be a queue for the loo. Dude, I actually have to go now. So what's the point of waiting in all these lines? Well, the point is to order people in some organized, useful way. The same thing can be applied to numbers. Right now, the way we've discussed rational numbers is as being in an unordered blob, kind of like the numbers in this Tupperware. What the number line does is it orders the number, all the rational numbers, in an organized, useful way, so now they can be compared. Traditionally, the number line looks like this, where we have smaller numbers on the left and larger numbers on the right. That's how we order the numbers in the number line. Now notice that we consider negative numbers to be smaller than positive numbers, and we have 0 in the middle. Now let me put this back in the fridge and let's do some examples. Let's start with the number 2. 2 is larger than 0 and 1, but less than 3, so we should place it to the right of 0 and 1, but to the left of 3. Next we have -3. -3 is negative, so we know it's less than 0. We can go even further and see that it's less than -1 and -2. So since the number line is ordered by smaller numbers on the left and larger on the right, -3 should be left of -1 and -2. And the number line isn't just for those pretty boy integers. We can also place fractions, decimals, and all other rational numbers on the number line. Hence, we can place 2.38, -3/4, 3 1/8, and all rationals in between. Alright, my part's over. Now it's time to check your knowledge with some practice problems. And what the heck? I'll stick around and help out. You know what they say. You can leave your math studio and go outside when you're dead. Okay, so the problem today is to classify the following numbers in as many categories as possible. First up, we have -3. Now, how many ways can we classify -3? Well, the first thing to notice is that 3 is a whole number, and by our definition of integers, integers are all the whole numbers and their negative counterparts. So -3 is the negative counterpart to the whole number 3. So negative 3 is an integer. And based on our picture of how all of our number types fit together, since negative 3 is an integer, that means it's also a rational number, which makes it also a real number. So negative 3 is also a rational number. And a real number. And that's it. But why is that it? Well, if we look at our other number types, we need to remember that the whole numbers are non-negative. No, there's no negative whole number. So what that means is negative 3 clearly isn't whole. Further, our natural numbers are all of our whole numbers 1 and up, meaning the natural numbers are also non-negatives. So negative 3 cannot possibly be a natural number. Lastly, we have the irrational numbers. So the irrational numbers are the numbers that cannot be written as a fraction. But because we said negative 3 is a rational number, that means negative 3 can be written as a fraction. So negative 3 is not irrational, meaning these are all the possible number types we can classify negative 3 as. Next up, we have 4.5 repeating. How many ways can we classify 4.5 repeating? Well, firstly, let's remember what this bar means. The bar means that this is actually 4.5555, where the 5 repeats forever. That's what the bar means, to repeat that digit forever. So, what do we know about repeating decimals? Well, we know from our previous work that repeating or terminating decimals mean that the number is a rational number. So, since 4.5 repeating is a repeating decimal, that makes 4.5 repeating a rational number. Then, once again, based on how our pictures are based on our picture of how our numbers fit together, since 4.5 repeating is rational, it's also real. And that's it. We know that's it because 4.5 clearly isn't an integer or a whole number because it has a fractional or decimal part. That's the part after the decimal point. And also it's not irrational number. It's not an irrational number because the irrationals cannot be written as a fraction. But because we know that 4.5 repeating is a rational number, it by definition can be written as a fraction. So these are the only ways we can classify 4.5 repeating. Here's number 3. We have negative 4.89375872357653487287 ... And it keeps on going like that with this decimal never terminating and also never repeating. So that language of never terminating and never repeating should remind us of irrational numbers because any non-repeating decimal is an irrational number. Therefore, we know our number here is an irrational number. And based on our picture, since it's an irrational number, it's also a real number. And we know that's it because we see that the irrational numbers do not intersect with any of our other numbers except for the real numbers. Meaning if it's irrational, it's not rational, an integer, a whole number, or a natural. So our number here is an irrational number and a real number, and those are the only ways to classify it. Number 4 is negative 9.76543221. How many ways can we classify negative 9.76543221? Well, unlike in number 3, this decimal is a terminating decimal. And we know that repeating or terminating decimals are rational numbers. So, negative 9.76543221 is a rational number. Then, based on our picture, we know that since it's rational, it must also be real. So it's also a real number. And then once again, because it's negative, we know it cannot possibly be whole or natural. And because it has this decimal part here, it also cannot be an integer. And then, once again, since it's rational, it's not irrational. So, the only ways to classify this number are as a rational number and a real number. Now, number 5 is a doozy. The number we need to classify number 5 is 1. How many ways can we classify 1? Well, we know that 1 is a natural number because by our definition, natural numbers are whole numbers 1 and up, and 1 is certainly 1 and up. So 1 is a natural number. And then, based on our picture, because it's a natural number, it's also whole, it's also an integer, it's also a rational number, and it's also a real number. So, 1 is also a whole number, an integer, a rational number, and a real number. The only thing it is not is an irrational number, and we know it's not irrational because it's rational. So these are the only ways to classify 1. Okie dokie, next up we have the number negative 9/3. How many ways can we classify negative 9/3? Well, let's see here. We know that negative 9 and 3 are both integers. So, if I could pick this up, there we go. Negative 9 and 3 are both integers. So, based on our definition, we know that negative 9/3 is one integer divided by another integer, which exactly makes it a rational number. So we know negative 9/3 is a rational number. And then, based on our picture, we know that because it's a rational number, it's also a real number. So, negative 9/3 is also a real number. And then because it's rational, it can't be irrational. Now, how about integer? Is negative 9/3 an integer? Well, by definition, an integer is any whole number and their negative counterparts. Is negative 9/3 a whole number or the negative counterpart to a whole number? Well, it might not look it, but negative 9/3, if we divide 9 by 3, is actually equal to negative 3. And negative 3, as we discussed before, is the negative counterpart to 3, which makes it an integer. So negative 9/3 is also an integer. And then, as we discussed before, negative 3, which equals negative 9/3, is neither a whole number or a natural number. So that means negative 9/3 is a rational number, a real number, and an integer. The important thing here is that we had to actually find out if negative, even though it looks like a fraction, we had to find out if it could be written as an integer, which in this case it can be. So the ways to classify negative 9/3 are as a rational number, a real number, or an integer. Okay, number 7 is the square root of 2, which equals 1.4142135 ... where this decimal never terminates and never repeats. So because it does not terminate or repeat, we know, like we did before, that it must be an irrational number. So the square root of 2 is irrational. And because it's irrational, that means we know that it's also real. So the square root of 2 is also a real number. Now, we know because it's irrational, it's not rational. So, if it's not rational, It certainly cannot be an integer, and it cannot be a whole number, and it cannot be a natural number. Therefore, these are the only ways to classify square root of 2, as an irrational number or as a real number. The last number we are going to try and classify is 5.678 repeating. How many ways can we classify 5.678 repeating? Well, like before, remember the bar means to repeat these digits forever. So 5.678 repeating equals 5.678, and keep repeating that pattern forever. So, based on what we've done before, we know that repeating or terminating decimals are equivalent to being a rational number. So because this decimal clearly repeats, that means 5.678 repeating is a rational number. And then by our picture, because it's a rational number, that means it's also a real number. And then, like we've done before, because there is a decimal part here, digits after the decimal point, we know that 5.678 repeating is not an integer, a whole number, or a natural number. And because it's rational, it's not irrational. So the only ways to classify 5.678 repeating are as a rational number and a real number. All right, now on to a new flavor of question, number 9. Number 9 reads, is 1/45th to the left or right of 0 on the number line? Well, remember the number line was our way of ordering all of the real numbers, where we put the smaller ones on the left and the larger ones on the right, where negative numbers are smaller than positive numbers and zeros in the middle. So all the negative numbers are to the left of 0 and all the positive numbers are to the right of 0. Well, 1/45th is positive. So that means it's to the right of 0 on the number line. So the answer is to the right. Now lastly, we have number 10, which asks, is negative 0.001 to the left or right of 0 on the number line? Well, once again, looking at our number line, we know that the number line is ordered such that negative numbers are to the left of 0 and positive numbers are to the right. So, therefore, since negative 0.001 is negative, we know that the answer is it is to the left of 0 on the number line. Or, to quote the Cupid Shuffle, to the left, to the left, to the left, to the left. Now kick. And that's it. Wow, what a rush! With this video in the bag, you should now be able to answer basic foundational questions about the 6 different types of numbers we went over today, as well as the number line. I will now put a cram sheet on the screen with the definitions we discussed. In the meantime, thanks for watching, and until next time, have a great day.